Good morning, everyone. Hope you're all doing well. So, let's take a look at what the next week or so is going to look like. Here we go. 192. Okay. So we're sitting right here at week 12. There's only 16, really 17 weeks of the semester. So everything's going to start to move really, really quickly now. It always kind of feels like that, especially after Thanksgiving, which is right around the corner. So this week we're going to be working on chapter 8, which is chemical reactions. And we will lecture on that. Hopefully we get that done this week, but I gave us a little bit of leeway so that we might be able to lecture into next week, because your test on the last 3 chapters, chapters 6, 7, and 8, is not going to be this Sunday. It will actually be, oh no, it is this Sunday. I don't know why that's here. Okay, scratch everything I just said, 11, 16. This needs to be here. So ignore everything I just said. So you will have a test this Sunday, and it will be over chapter 6, 7, and 8. And that includes, or the test can be taken anywhere between Sunday through Monday, like we've said before. After this test, then we just really have 3 chapters left, and then we're done with the semester. I mean, it's going to go quickly. I would say this chapter is probably the most, for everybody, but for a lot of people, it tends to be the most challenging just because it's pretty math-based. So, you know, you do the best you can, but remember you do have a grade replacement. So your lowest test grade will get dropped. If you do better on the final will replace it. So let's say you've got A's on all your tests except one test you got like a D on. And then on the final, you end up squeaking by with the B. The B will cover the finals grade, and then the B can also replace the D that you got. All right, so let's get into chapter 8. I'm going to replace that syllabus too. Let me make a note. Updates. So chapter 8, quantities and chemical reactions. So this is going to take the last 2 chapters and sort of mix them together in an applied way. So global warming, too much carbon dioxide. What does this mean? Okay, well, when we combust fossil fuels, so fossil fuels are anything that have carbon and hydrogen mixed with them. We use octane or gasoline in our car. We use propane, butane to cook food and ignite lighters. But anytime we do that, we are going to produce carbon dioxide and water. So this is a combustion reaction. Carbon dioxide is, so these little guys right here are relatively effective greenhouse gases, which means that they help to absorb or keep heat within our atmosphere. So the greenhouse effect, we've got light coming in, and then a certain amount of heat will then radiate off the earth and bounce back out. Now, when we have an excessive amount of these greenhouse gases, it creates almost like a trap or a barrier where the heat will try to escape and then it comes back down. So we create this sort of positive feedback system where we continue to have heat increasing within the atmosphere. So as far as how that relates to chemistry, this would be a balanced equation right here for the combustion of octane. So I have 2 octanes. They're going to combine with 25 diatomic oxygens to produce 16 CO2 molecules and 18 water molecules. So that, you know, for 2 octane molecules, I get 16 CO2s. That's pretty efficient in its CO2 production. So since we know the world's annual fossil fuel consumption, because we know how much fossil fuel has been sold, we can use that equation to actually figure out how much CO2 is being produced based off of the chemical equation. And this calculation of calculating CO2 from the amount of gasoline or octane that we're using is known as stoichiometry. So here's the word stoichiometry, which is just a fancy way of saying the numerical relationship between chemical quantities in a balanced chemical equation. So you need a balanced chemical equation. You can't do stoichiometry without a balanced chemical equation. I will either give you the balanced equation or you will have to balance it yourself, or sometimes you may even have to write the equation. But the nifty thing about a balanced chemical equation is when it has those coefficients in front of it, we can actually use those coefficients as a molar relationship to predict how many products we would need if we had a given amount of reactants. We can predict how much reactant we would need if there was a certain desired amount of product, or I can decide how much reactant, one reactant is needed in order to completely react with another thing. So we're going to go to this baking relationship, because at the end of the day, stoichiometry and the process of stoichiometry is really similar to reading a recipe. And when we are making something like, let's say here, we're making pancakes. I don't say flour plus egg plus baking powder equals pancake. Because how much flour, how many eggs? So we have to actually say, I need 1 cup of flour. So we're going to think of that 1 as like our coefficient in our balanced equation. Here, I need 2 eggs. It's not enough to just say eggs. I have to actually explicitly say I need 2 eggs. And I need 1/2 teaspoon of baking powder to produce 5 pancakes. So let's say we want to talk about the relationship between eggs and pancakes. Well, 2 eggs will yield 5 pancakes. And that's coming right off of here. 2 eggs for every 5 pancakes. Okay. If I want 5 pancakes, I can't have 1 egg. 3 eggs is going to be too much. I only want to use 2. So this right here is showing us a conversion factor from eggs to pancakes. Oh, excuse me. Sorry, this morning I cannot stop yawning. So we can write the relationship like this. For every 2 eggs, we get 5 pancakes. Or for every 5 pancakes, I need 2 eggs. So if we have 8 eggs, assuming that we have more than enough of all the other ingredients, how many pancakes could we make? You may be just sort of doing this math in your head. Oh, if I have 8 pancakes, or 8 eggs, obviously I'd make 20 pancakes, right? I just multiply the numbers together and divide by 2. Well, let's set it up in dimensional analysis. Okay, so we said our conversion factor was 2 eggs for every 5 pancakes. If I have 8 eggs, I'm going to multiply it by that conversion factor, where I put the 2 eggs on the bottom and I put the 5 pancakes up on top. And then what I see is that my unit of egg will cancel. We take our 8 times our 5 and then we divide it by 2, which is telling us, hey, we get 20 pancakes. So based off of this here, I want you to tell me how many pancakes could you make if you have, let's say you have 30 cups of flour. Okay. So go ahead and figure out with 30 cups of flour, how many pancakes you can make. So Suzanne's already got an answer. So what we want to do here is we got to figure out what the relationship is between flour and pancakes. So here's my flour, here are my pancakes. For every 1 cup of flour, I am equivalent to 5 pancakes. Pancakes. So using that in dimensional analysis, the 1 cup of flour needs to go on the bottom because we need those to cancel, and it will produce 5 pancakes. We multiply them together and we divide by the 1, and we do in fact get 150 pancakes. Easy peasy. And it always seems to freak people out when we try and convert it over to stoichiometry, but stoichiometry is the same thing. So let's look at a balanced equation. So we've got the balanced equation of the synthesis of ammonia. So hydrogen is going to combine with nitrogen to produce ammonia. Hydrogen is a diatomic, so we do put a 2 there. Nitrogen is also a diatomic, so we put a 2 there. When we balance this whole thing out, we would have a 3 in front of the hydrogen, a 1 in front of the nitrogen, and a 2 in front of the ammonia. So 3 of these molecules combine with 1 of these molecules to produce 2 of these. So some things that we can write for this balanced equation. 3 hydrogen molecules are needed to produce 1 of these ammonia molecules. 1 of these nitrogen molecules are needed to produce 2 of these ammonia molecules, or we could also see a relationship here of 3 hydrogen molecules will need to combine with 1 nitrogen molecule. So all of these things are now conversion factors. So these relationships allow me to hop from 1 compound into another compound off of the equation. And these numbers are going to be unique for every balanced equation. So if I'm using a different equation that also has hydrogen in it, it may not have the same relationships. So if we look here, let's say we have 3 moles of nitrogen and more than enough hydrogen. How many or how much ammonia can you make? So one thing that I like to do when I'm working on these problems is I've got nitrogen, I've got ammonia. It says I have more than enough of the hydrogen. So I'm really just going to be using my nitrogen and my ammonia. We can sort of ignore this because we said we have more than enough. Now, obviously, we're not ignoring it in the extent of the full chemical equation because we need it there in order to balance it properly, right? In order to put the 3 there and the 1 and the 2. But at this point, I can just sort of put it into the background. And the only thing that I'm going to be looking at is my relationship between nitrogen and ammonia, which is a 1-to-2 relationship, right? There's no coefficient here, but we can infer that there's a 1. So for every 2 moles of ammonia, I will have 1 mole of nitrogen. We said we're starting with 3 moles of nitrogen, so let's put that down, 3 moles of N2. And I use my relationship, 2 moles of NH3 for every 1 mole of N2. Then N2 will cancel and we'll be left with just moles of NH3, specifically 6. So you're seeing how this is sort of like baking, right? We're going from the eggs to the pancakes. We're going from the reactant to the product. So I'm going to give you another one with this balanced equation here. Give you 2 minutes to work on it. So say that we're given 9.26 moles of hydrogen gas. I want you to find how much nitrogen gas you would need in order to combine with all of that hydrogen gas. Okay, so in this situation, we're just trying to see the relationship between the two reactants. So I've got 3 of this and 1 mole of this. I'm not making those numbers up. I'm literally just pulling them off of the balanced equation. So if I have 9.26 moles of H2, and you're going to want to get in the habit now of writing not just the word mole, but mole of something specific, because we're going to have moles of different things. So for every 9.26 moles of H2, okay, so we want to put the hydrogen gas on the bottom. So we'll put 3 moles of the H2 on the bottom for every 1 mole of N2 on the top. We take our number, the 9.26, and we divide it by 3, which will give us, and we go with 3 significant figures here, 3.09 moles of hydrogen gas. Any questions on that? And how we can use a balanced equation to go from one material to another using those coefficients. Let's keep moving on. All right, let's skip through there. So those last equations were relating moles and moles. How often are we given things in moles in real life? Not very often. Usually we're given things in a mass value. So when trying to go from the mass of one compound into the mass of another compound, you are going to use this flow chart here. So have this available or written down somewhere, but it's mass of A into moles of A, into moles of B, into mass of B. A is standing in for compound A. That's what your starting information is, or your giving information. B is where you're trying to end up, so your ending compound. How do we get from mass of A into moles of A? We use the molar mass of A. That's back in chapter 6. Okay, so molar mass will get us from this to this. This is something you'll have to get from the periodic chart. And if it's a compound, you have to calculate it. Moles of A into moles of B, this is that ratio from the balanced equation. This is what we've just worked on, okay? So that's magic step with the coefficients. Right in there, coefficients. All right, and then B, moles of B back into mass of B. This is, again, we use molar mass, but in this case, we use molar mass of B. So A is over here, B is over here. So mass to moles to mass, or grams to moles to moles to grams. This is going to always be your flow chart. Now, those last two problems we were working on, I didn't give you mass, I gave you moles. So we just started here on the flow chart and ended here on the flow chart. So we only had to do one hop, right? When we're given mass, we're going to need to do 3 hops. 1, 2, 3. So let's look at this one here. We have 5.0 times 10 to the 2 grams of pure octane. We want to know how many, I believe they're trying to figure out how many grams of carbon dioxide are there. So we know something about octane. We're trying to figure something out about carbon dioxide because the octane is relatively inert in the atmosphere. It's the CO2 that's given us troubles. So if I have 5.0 times 10 to the 2 grams of pure octane, I'm going to go grams into moles, moles of this, and hop over to moles here, and then back into grams. So let's see that set up here. So grams of octane into moles of octane into moles of CO2 back into grams of CO2. What is happening here? This step is going to be molar mass of C8H18. All right, that's what this value is here. 1 mole of octane is 114.3 grams. What's happening in this step to go from moles to moles? This is the coefficients. Okay, so 16 to 2. So they're saying for every 2 moles of octane, we're going to get 16 moles of CO2. And then from there, we're going from moles of CO2 into grams of CO2 because I don't want to know how many moles of this I have. I want to know how many grams. This is molar mass of CO2, which is 44.01. Okay, so grams to moles to moles to grams. Don't get creative with this. Don't try and do it a different way. Just solve it in this setup and you should be good. So let's take a peek at how they got through this, and then we're going to do some practice, or you will all do some practice. Okay, so we started with our given information was about octane. We converted grams of octane into moles of octane. So the mole went on the top and the mass went on the bottom. Those cancel. Then we used the coefficients, and we set the coefficients up in a way that octane was on the bottom because I want to get rid of octane. I want to move into CO2. From there, we use the molar mass of CO2 because octane is gone. It's like we've already hopped out of that. We're away from that. So we're just talking about CO2. So we need to use the molar mass of CO2 to then get us into our grams of CO2. And in this case, it's 1.5 times 10 to the 3 grams of CO2. So for every 5.0 times 10 to the 2, or this is 500, for every 500 grams of octane, we will get 1,500 grams of CO2, lots of CO2. Any questions on that setup thus far before we go ahead and work through? I'll work through one practice problem with you and then I'll give you all one. Questions? No? Okay. So let's say, how many grams of aluminum oxide are produced from 9.64 grams of O2? And I'll give a balanced equation. Al plus O2 gives me Al2O3. Yeah, give myself a little more space. Al2O3. Okay, and we've got 2 here, a 3 here, and a 4 here. So if this hadn't been given to you, you would have needed to make a balanced equation. So we're given something on oxygen, and we want to find aluminum oxide, which is the product. So I'm going to write a flow chart. Again, you don't have to write a flow chart every time you solve these, but just in the beginning here, so you know, like when you go back to study, where did all these numbers come from? So we're going to start with grams of oxygen. And I want to convert that into moles of oxygen. It's important that you see that it's a diatomic, okay? So if it's written as an O2, make sure you're including that too. Then we want to go to aluminum oxide, so we'll go to moles of Al2O3. And then from there, we'll go to grams of Al2O3. So starting with our given value, we have 9.64 grams of O2. 9.64 grams of O2. My first step is to go from grams of O2 into moles of O2. So in order to do that, I need the molar mass of not just O, but O2. All right, so if it's a diatomic, make sure you're taking that into account. So for every 1 mole of O2, I am 32 grams of O2, because it's a diatomic. Next step is to go from moles of O2 into moles of the product. So this is where we use the balance equation in the middle step here. 3 for every 2. This is the only place you use those coefficients. Don't put coefficients here. Don't put coefficients over here, okay? So I don't say, oh, when I'm starting to solve this, I don't go, oh, but I have 3 of the oxygen, so I'm gonna put a 3 here. We leave the coefficient for the middle step. We don't wanna double up on our coefficients. So in this case here, I've got moles of O2 on the bottom because I wanna get out of that. And then I have moles of my Al2O3 up top. The relationship 3 moles of O2 for every 2 moles of my Al2O3. Last step is to use the molar mass. So the molar mass of aluminum oxide. So to get from here to here, I use molar mass of my Al2O3. I'm going to put the mole on the bottom because I want that to go away. And then on top, I'm going to put the gram because that's where I'm headed, grams of Al2O3. The mass of this thing for every 1 mole is 101.96. 2 aluminums added to 3 oxygens. So when I'm doing the stoichiometry, I don't think, oh, when I'm going this way, I divide, and when I go this way, I multiply. And I just set it up and make sure my units cancel. So grams of O2 cancel with grams of O2. Moles of O2 are going away with moles of O2. Moles of the compound or the final product, aluminum oxide, are canceling with moles of the aluminum oxide. So now we just need to plug this into our calculator. So take everything that's on the top and multiply it. So we've got 9.64 times, we've got a 2 times a 101.96. Then we're going to need to divide by the bottom stuff. So divide by 32. And then we also need to divide by a 3. All right, and I end up getting 20 point, how many sig figs? 3 sig figs. So 20.5 grams of the Al2O3. So if I have 9.64 grams of oxygen, I could, as long as I have an excess amount of aluminum, produce 20.5 grams of Al2O3. Questions on this? No one's got their camera on today. Everybody's hiding. I get it. I understand it's been a rough last like 5 days, but put in the comments if you need help with this. Otherwise, I'm going to give you an example. Okay. Maybe you don't even know if you need help yet. Okay, I'll give you the example. And if you come to a place where you're having trouble, please let me know. Because I think that this is one of the trickiest things for people to do if you're not math savvy. And people who are good with math, they kind of like these. So I'm going to do just a totally different problem. Use a different equation and everything. So how much what do I want to do here? Sorry, hold on. I've got to think of an equation. Let me write an equation first. Help me out. I don't know what to say. All right, we'll do NaCl plus CaCO3 produces CaCl2 plus Na2CO3, and we need a 2 here. Okay. How many grams of CaCl2 are produced from 103.7 grams of NaCl? So here's your balanced equation. I'm saying how many grams of CaCl2, we're talking about this, are produced from 103.7 grams of this. So it's 838. I'm gonna give y'all 6 minutes to work through this because you're gonna have to calculate some molar masses. All right, let's come back together. So we've got this balanced equation. In this one, we've got 2 reactants and 2 products. It's okay. You could have 3 reactants and 10 products. Once it's balanced, you really only have to look at the 2 things that specifically you're talking about in the problem. So how many grams of this are produced if we have 103 grams of this thing? So I start with my given information, as always. 103.7 grams of NaCl. Now I want to convert this into moles. So 1 mole of NaCl weighs roughly 58 grams of NaCl. Next, I want to go from here to here. So the relationship is 2 moles of this will produce 1 mole of this. So 2 moles of NaCl for every 1 mole of CaCl2. Final step is to use my molar mass of CaCl2. So for every 1 mole of CaCl2, I'm going to have a mass of 110.98 grams. Double check that everything cancels just the way you like it. And then you run it through your calculator, which I have not yet, so give me just a second. So we've got 103.7 times 110.98 divided by 58 divided by 2. Now, if you said, oh, I used 58.1 or I used 111, that's okay. You will get close enough. So I got 99.2. If you had 99.5 or 99.0, that's okay. There's a little bit of variation with this is all right. Any questions from anybody out there? Are you getting this? Yes, no. It's so quiet today. Okay, well then we'll keep moving ahead. So in every situation that we've talked about so far, we've only been looking at 2 things, right? Like one of these, 1 reactant and 1 product. Well, now we're going to talk about this thing called a limiting reactant, theoretical yield, and percent yield. So let's talk more about pancakes. So let's say we've got our pancake recipe. But things are a little bit different now because you go into your pantry. Like let's say you have a bunch of friends over and you're going to make pancakes in the morning and you want to know how many pancakes you can make with what you've got left in the cabinet. Who's done that before? Tried to like make as much as you can with as little stuff in the fridge. So in this case, you go to the pantry and you find that you have 3 cups of flour, you have 10 eggs, and you have 4 teaspoons of baking powder. And you want to figure out, well, how many pancakes can I make? So what you need to do is decide or calculate how much of each of these ingredients they can yield in pancakes. Because when I'm talking about 3 cups of flour to 10 eggs, it's like talking about apples and oranges. They're not in the same units. They don't have the same weight. So I'm going to take each of my reactants or each of my ingredients, and I'm going to convert them into how many pancakes they could potentially make. So if I have 3 cups of flour, and from my recipe, 1 cup of flour yields 5 pancakes, I could potentially make 15 pancakes. Okay. If I have 10 eggs, I could make 25 pancakes. And if I have 4 teaspoons of baking powder, I can make 40 pancakes. So you may be thinking, yay, we can make 40 pancakes. No, we're only as strong as our weakest link, right? We can only make as much as the least reactant can make, or this is known as a limiting reactant. Limiting reactant. It's the reactant that is holding back the chemical equation. So this is not possible. This is not possible. We can only make 15 pancakes. Yeah, you've got extra eggs. So I don't know, make an omelet. And you've got extra baking powder, you know, put it in your fridge because it stinks because you're only making 15 pancakes. So let us move on here. Here we go. Okay. So this is going to be known as, there's a couple different terms up here. This is the limiting reactant, the thing that's holding the equation back. So the flour is the limiting reactant. You will give a name for limiting reactant. So this would be flour. The theoretical yield is the amount of product that you can produce from that limiting reactant. So in theory, I could produce 15 pancakes. It's definitely not this, and it's definitely not this. This is like, you'd have to get more flour in order to make that many pancakes. So limiting reactant is the compound that's holding it back. Theoretical yield is the amount of product from that compound. So I don't know if you've ever cooked pancakes, but there's always like the throwaway pancake. So suppose we cook our pancakes, but we burn 3 of them because you can't get the butter just the right temperature. And then you start to get into your groove and somebody bangs your elbow and you drop one on the floor. I would probably pick that up and eat it anyway, but in this case, they're leaving that one, okay? So what happened was we could produce 15 pancakes, but when we finished, we were only able to produce 11 pancakes because 3 of them burned and 1 of them fell on the floor. So the 15 pancakes would be your theoretical yield. In theory, you could make 15 pancakes. The 11 pancakes is known as your actual yield. That's how much you produced in real life. Where does the actual yield come from? This is going to be a number that is either given to you or you would run experimentally. Obviously, we're not meeting right now, so we're not going to be doing any experimentals. So on your test, that will just be a given number to you. I'll say, hey, this was what actually was produced. So then we have this other term called percent yield. And they don't really have do they have the equation anywhere, written anywhere? Actual, okay, I don't know why they don't have it written down. I'll write it down over here. No, I'm actually gonna go. Over here. Okay, so we have limiting reactant. We have theoretical yield. We have actual yield. And then we have percent yield. Now, percent yield is going to equal your actual yield over your theoretical. And we're going to multiply this by 100 because it's a percent. Okay. One way to remember this, A over T. So A comes before T in the alphabet. So put A on top. So in order to figure out the percent yield, you take your actual, which will be your given, and you divide it by your theoretical. So in the case of the pancake situation, all right, we had 11 pancakes. We could have produced 15, so you were 73% in your percent yield. So 73% of the potential pancakes were made. The other 27 didn't happen. So let's do a problem. I don't like these problems here. I'm gonna get rid. I don't want to do those. I'm gonna make one up because. So back to the aluminum oxide problem. We've got Al plus O2 produces Al2O3, 2, 3, 4. What is the theoretical yield if you have 19.4 grams of aluminum and 7.85 grams of oxygen. So theoretical yield, right, is how much product I could make. Now, in this instance, I'm given a value for my aluminum and I'm given a value for my oxygen. So just like when you were making those pancakes, you had to take each of these values and convert them into the product to figure out which one produced less. We've got to do the same thing here. So we'll start with the aluminum. So you're doing your stoichiometry, all that stuff we did in the last couple problems, you're doing it, but you have to do it twice. We have to do it for the aluminum and for the oxygen. So for the aluminum, I have 19.4 grams of aluminum. I need to convert this into moles. So for every 1 mole of aluminum, I am 26.98 grams of aluminum. For every, now we use our stoichiometry because we're going to hop from here to here. So for every 4 moles of aluminum, I produce 2 moles of my product. And then let's convert it back into grams. So for every 1 mole of the Al2O3, oh, what did we say it was? I forgot. Oh, 1.96 grams. Okay. So plugging this into our calculators, we get 19.4 divided by, no, I'm going to do all the tops first. 19.4 times 2 times 101.96 divided by, I've got a 26.98. And I have to divide it by 4. Okay, so in theory, I could produce 36.7 grams of Al2O3. We're not done though. We have some information about oxygen. So I have to go through the same process, but using the oxygen value. So I have 7.85 grams of O2. And it's not enough to look at this and say, oh, well, you know, this is obviously the limiting reactant because I have less of it. Yeah, but this is a lighter material than aluminum, so you really don't know until you convert it into the same thing. So for every 1 mole of O2, remember that's 32 grams. And in our relationship, for every 3 moles of O2, I get 2 moles of the Al2O3. And then we can use this same value here for every 1 mole of the Al2O3. 101.96 grams Al2O3. So these problems take a while. They're time consuming. 7.85 times 2 times 101.96. Okay, we'll divide it by 32 and we'll divide it by 3. So this one says 16.7 grams of Al2O3. So O2 is our limiting reactant. The aluminum in this case would be known as our excess reactant. What we have more of or too much of. Okay. This value over here is the theoretical yield. So in theory, we can produce 16.7 grams. Now let's just add up a part B to this problem. Part B, what is the percent yield if the actual yield is 10.2 grams of Al2O3? So here, we're trying to figure out how good were they at running this equation or this reaction. Well, we know our actual yield, and then our theoretical yield was solved from the previous part of the problem. So percent yield, remember, is A over T times 100. Or our actual, which is given to us, 10.2 grams, over the theoretical 16.7 grams times 100. So 10.2 divided by the 16.7. So 61.1%. So not great, not a great percent yield. How's everybody feeling with that? Confident? No? Radio silence. Oh, I got a thumbs up from Harley. Okay, awesome. So obviously we want to do some more practice on this. So let's do 902. Oh, good, Lyric, okay. These problems just take so long. They just take so long. Real quick, I'll give you a balanced equation. Let's say we've got magnesium, do something relatively simple. So magnesium comes together with sulfur to produce magnesium sulfide, which is MgS. No, I don't want to do that one. I don't want to do that one. I want to do something that has a coefficient in it. Let's do N. Mg3N2. Okay, so this is our equation. So we're given that we have 6.1 grams of Mg and 5.2 grams of N2. I want you to find the theoretical yield. Find which one's the limiting reactant and find the theoretical yield. I'll give you to like 9:11, so 6 minutes, and then I'm gonna plow through it. Give it a Okay, so when we're given a problem where you have two amounts, I'm asking you for the theoretical yield, you're gonna have to go through the process of stoichiometry for each one. So first guy here, we've got magnesium. So 1 mole of Mg is going to be 24.3 grams of Mg. And we got to relate. And if it doesn't tell you like where you're headed with eliminating, you're going to the product. So just go towards the product. So we've got a 3-to-1 relationship. 1 mole of the product for every 3 moles of the magnesium. And then last step, for every 1 mole of MgN2, Mg3M2. Well, what is your mass, Mg3M2? 100.9 grams of Mg3N2. Okay, then we're going to do the same thing for the bottom guy. I'm going to do the setups first and then I'll calculate it. So for this one, 1 mole of N2 is equivalent to 28 grams of N2. Why is it 28? Because it's got the 2 there. Don't forget that. This is a 1-to-1 ratio, right? For 1 mole of N2, we get 1 mole of the product, Mg3N2. And then the last step, for every 1 mole of the product, Mg3N2, we can just use the molar mass that we calculated from the previous one, 9 grams G3N2. So let's put these into the calculator and see what we're going to get. So 6.1 times 100.9 divided by 24.3 divided by 3. So this will produce 8.4, only 2 sig figs, 8.4 grams of the Mg3N2. This bottom guy, 0.2. This thing can produce 20.2 grams of the Mg3N2. All right, so limiting reactant here is the Mg. Reactant, sorry for the handwriting. And this is the theoretical yield. In theory, we could produce 8.4 grams of Mg3N2. We will do some more practice with this when we come back to meet on Wednesday, and we'll do some more with percent yield. Okay, so I'll let y'all go. If you've got a question, feel free to stay around. Otherwise, enjoy the next couple days. Email me if you need any help with anything. Bye, everybody.